Hey folks, so today we're going to be doing a question about fluid dynamics, and we're going to be talking about the pressure at the bottom of the Marianas Trench, which is a trench that James Cameron, the director, the producer of Titanic and Avatar, he visited this trench, and he measured it, or he knew it was 11 kilometers deep, and he went down there basically in a steel sphere that had a diameter of 109 centimeters and walls that were 6.4 centimeters thick. So what we want to do in this situation is they want us to find the total pressure force exerted on the sphere at the bottom of the trench. And basically, they don't want us to calculate this using buoyancy, and that's because we don't have to worry about the vector forces here. So the main equation we're going to worry about is force over area. And the term that we're going to want to find is the force. So F is equal to PA. And now basically the name of the game is, can we identify these two specific terms? If we can get expressions for these terms, then we've basically solved the problem and we can get the answer we want. So I'm going to get pressure first, because why not? And the way we're going to get pressure is to use Bernoulli's equation. What we're going to do is we're going to solve this in two different situations. We're going to solve it for the surface, and we're also going to solve it for the bottom of the trench. So surface first, let's just write down the equation. What we find is that at the surface, we're going to call this y equals 0. It's going to make our life easier, and you don't have to do it this way, but it makes a lot of the calculations simpler. So at the surface, y equals 0, so that term goes to 0. And we're going to assume that the water is not moving around. We're going to assume that it's stationary, which is not entirely true, but it's a valid assumption to make. So then what we get is that the pressure at the surface is actually the constant value that we know exists for these kind of systems. So that's great. Keep that in the back of your head for now, but we're going to come back to that in just a bit. Again, we're going to do the same thing now, but for the bottom of the trench. And again, we're going to say that the water is not moving. And this time, we're going to have a specific value for y, and that's going to be the depth of the trench. So the depth of the trench is 11 kilometers. So just writing that down now. P bottom plus rho g y depth equals constant. But we also know that the constant is equal to the surface pressure. That's what we calculated at the line above. So we can just say that's P surface. Now, the way we've defined our system, downwards is negative. So we're going to pick up a negative value from y depth. So this is all going to work out in the end. So we have our expression for pressure, basically. What we want is the pressure at the bottom of the ocean. So the P that we want to find is just this P, and that's equal to the surface pressure minus rho g y depth. where, again, y depth is equal to minus 11,000 meters, because y goes negative as we go down. So we've got P, great. Now what we want to do is basically we want to find A. So A basically is just every point in the sphere that is in contact with the water, and that's just the surface area. So A is equal to 4 pi r squared, but we know that r is just half the diameter, so that's equal to 4 pi d squared over 4, which is equal to pi d squared. So we have our expression for area now, which I'm just going to simplify to be pi d squared. Now, the only thing left to do is to calculate d, and we do that by looking at the setup of this sphere. So we have some internal diameter, and we want to calculate the full diameter. We want to calculate all of d. So we got to include this extra term, which is the thickness of the walls, because the water will act on the outer surface of the sphere. It's not going to act on the inside surface. So the diameter is equal to the internal diameter, which is 1.09 centimeters, 1.09 meters, 109 centimeters, plus twice the thickness of the walls, which is 0.0064, which is just equal to I gotta use my calculator for this. .218, I think. I included an extra 0 here when I didn't need to. Again, converting between centimeters and meters. So again, we have our expression for D now. Let's calculate pressure now. So P is equal to P surface minus rho g y depth. Now, if you've gotten to this point, the chances are you're going to get like 9 out of 10 out of your questions. Sorry, like 9 out of 10 in this question, because you've like basically set it up properly. But there are certain values that they're probably going to give you. And if they don't give it to you, then it's kind of hard to just know them off the top of your head. So you don't need to feel too bad if you don't know any of these. But it just so turns out that the surface pressure at the top of the ocean is about 101.3 kilopascals, and that the density of salt water in the ocean is 127 kilograms per meter cubed. That just happens to be what it is. So yeah, if you didn't know these, you would have probably gotten part marks all the way through, or they would have given this to you in the exam. So plugging in those, and of course gravity is 9.8. Plugging those into the equation for pressure, we get that pressure is equal to 1.11 times 10 to the 8 pascals. And the area is equal to pi d squared, which is about, let's see, pi times 4.66. So force is equal to 4.66 times 1.11 times 10 to the 8 newtons, because we're working in standard units, which is 5.17 times 10 to the 8 newtons. Yeah, so that's basically the answer. And I'm just going to clear it up a bit so that it's presentable again. You didn't have to know the exact values for P surface, rho, and Y depth, but if you did know them, then you're going to get full marks. Otherwise, they would have had to give that to you in the exam, because I don't think it's fair if you just have to memorize those. So yeah, hopefully this is helpful. Let me know if you want more videos like this.